Consider this curve right here. This curve is perfectly smooth. It passes the vertical line test, so it is the graph of a function. Because of that, I know that I can express it as a function in terms of x. And here it's the expression. You can see that f of x is equal to x to the third minus 4x, and this expression represents this graph. New vocabulary for this section is another name for this expression right here. This expression will be referred, or any expression f of x equals something in terms of x, that will be expressed as an expression in rectangular form. So rectangular form. So every time that you see in the book or anybody saying, oh yes, this is the rectangular form of this function, simply speaking, the rectangular form, that just means the expression that represents the curve as a function of x. So that just means f of x equals. Every time that you see f of x equals, you can refer to it as the rectangular form of the function. So right now what we have is a curve with its rectangular form as f of x equals x to the third minus 4x. And you know that in order to get a point on this curve, I have to specify an x value. So if I pick an x value, let's say 1, then in order to get its y value, I just go back to the rectangular form of the function. I substitute 1, so in this case 1 minus 4 equals negative 3. And that, putting these two together, immediately gives me a point on the graph. So then I know on the graph right here that that point corresponds to this location right here. So that point is going to be right here at the lowest part. So this will be the point 1 comma negative 3. So this is pretty much the only conception that we have right now when it comes to representing a graph algebraically and finding a point on that graph. We pick an x value, we plug in the x value into the expression of the graph, and we work out the y value. Then we go ahead and we find the location of that point on the curve, in this case, right here at the bottom. What I want to do today is to show you another way to represent this graph. And this other way is called the parametric representation of the graph. In parametric forms, I just don't have one expression representing the graph. I will now have two expressions, one expression for x and one expression for y. Each of these expressions will give me, let's say the expression for x will give me the x values for a particular point, and the expression for y will give me the y value for that particular point. The only thing is that now, by having one expression for x and one expression for y, I am going to have another variable involved. So there are going to be three variables, x, y, and now t. Let me show you exactly what that means. For example, the parametric form of this graph right here on the left, the parametric form will be like this. The equation or the expression for x will be, let's say, t to the third. As I said, the x values will have its own expression, in this case t to the third. And the y values will be t to the 9 minus 4t to the third. So notice over here how the x values have its own expression, t to the third, and the y values its own expression, t to the ninth minus 4t to the third. Here, as I said before, I now have three variables involved. I have the typical x and y, but now we have introduced a third variable, t. This variable is what is referred to as the parameter of the equations. T is the parameter. Okay, so this will be over here, parameter. And t has its own domain. In this case, the domain of t corresponds to all real numbers, but it doesn't always have to be the case. Sometimes t is going to be restricted. It's going to be, let's say, a number that goes from a to b only, whatever a and b are. So sometimes t is going to be infinite, the domain of t, but sometimes the domain of t is going to be restricted to an interval. And as we go along in the study of this section, I am going to show you various examples, and all of these examples will involve a different domain for the parameter t. So typically though, the way that this will be expressed is as follows. Because x is a function of t now, then it is very typical to, instead of just say x, express it in function notation, x of t, and the same thing with y of t. It doesn't have to be that way. You could have left it as x equals t to the third, y equals t to the ninth minus 4t to the third. Honestly, that's acceptable, and in books are different, but I like to remind myself that x now is a function of t and y is a function of t. So now these expressions are going to give you the coordinates of every single point on this curve right here. And because of that, it is very nice to actually rewrite these expressions in the following form. C of t, you can say, is going to be equal to a big order pair, and the order pair will consist of the x values as given by t to the third and the y values as given by t to the ninth minus 4t to the third. So this is a great way to express the curve in parametric equations. C stands for curve, T represents the parameter. You don't always have to use T. The reason why T is preferred or is extremely typical when dealing with parametric equations is because T reminds you of time. And I'm going to, in just a few minutes, I will tell you, we're going to have a discussion as to why time. But anyways, that's why t reminds us of time. The x coordinate is given by t to the third, so t to the third is going to go first, and here you have the classic brackets for the coordinate point. Then you have comma in the middle, and then right here you have the expression that is going to give you the y values. And then it is very typical to put another comma and to express pretty much the domain of the parameter t. So in this case, t lives within the real numbers. So how do I get a point on this curve right here? Well, in order to get a point on that curve, you're going to start choosing values for t. So now instead of choosing values for x to get y, that's the way that it works whenever you're dealing with rectangular form, right? If you're dealing with the rectangular form of a curve, you choose values for x and you find y. But in parametric form, you don't do that. You actually choose values for t, you plug them into the expression that will give you x and the expression that will give you y, and that's how you find the coordinates of that point. So let's say that I choose the value for t equal to 0. Then the x value will be, remember that x will be x of 0, which is 0 to the third. That's going to give us 0. and then y of 0 will be 0 to the ninth, so 0 minus 4 times 0 to the third, that is going to give us 0. So the conclusion is that when t is equal to 0, the point that corresponds to that on the curve will be the origin. So right here, this point right here corresponds to the parameter being 0. When it comes to t equals, let's say, 1, then again, x of 1 will be 1, and then y of 1 is going to be 1 minus 4, negative 3. So then the point that corresponds to the parameter being 1 will be the point 1 comma negative 3. And this is this point right here. So this point corresponds to the parameter t equals 1. In the same way, we can choose negative numbers. So let's say negative 1. When t is equal to negative 1, the x value, x of negative 1, will be negative 1 to the third, that will be negative 1. And then y of negative 1 will be negative 1 to the ninth minus 4 times negative 1 to the third. That will give us very nicely negative 1. Then over here, plus 4, that is going to be 3. So therefore, the points that corresponds to t equals negative 1 will be negative 1 comma 3. And this is exactly this point right here, negative 1 comma 3. And that happens when t is equal to negative 1. So you notice that all that you have to do is find values for t, assign values to t. Again, values though in the domain of t. So in this case, t corresponds to all real numbers. So just pick any value for t, any real number, plug them into the expression for x and the expression for y, and that's how you're going to get every single point on this curve right here. So you may be thinking right now, why is this any better than what I had it before, right? Before the graph, the function, the curve was expressed in rectangular form as a function in terms of x. I would choose values for x, plug them into expression, and I will get y. Why is parametric representation any better? Doesn't that sound even more difficult? I have now two expressions, one for x, one for y, and I have a third variable, a parameter t. That seems more complicated. So how is this an improvement over rectangular form? There are two reasons why this is a tremendous improvement over just a rectangular form representation. Number one, the curve doesn't have to be the graph of a function in order to be able to express it parametrically. Whereas in this case right here, if you want to be able to express a curve in rectangular form, that means you want to be able to write y in terms of x, just like this. For you to be able to do that, that means that you must have a curve that is a function. If the curve is not a function, you're stuck. You cannot find an expression in terms of x to represent that curve. When it comes to parametric equations, that doesn't have to be the case. I can have something as bizarre as this. Imagine a curve like that. How pretty. This is your x and this is your y. Now, if you look at this curve right here, it is not a function. It fails the vertical line test. However, I can still find a parametric representation of this curve. I should be able to find a c of t with equation for x in terms of t, an equation for y in terms of t. That is going to give me every single point on this curve. And t is going to have some domain. I'm going to put over here, t is going to have a domain. And that, as I said before, that domain could be all real numbers, but that domain could be bounded, could be an interval. The point is that this curve doesn't have to be a function for me to be able to express it parametrically. And that's a huge improvement over rectangular form. With rectangular forms, I am restricted to functions. With parametric form, I am not restricted to function. So that's improvement number one. So we can write here that curves may not be functions. They don't have to be functions. So that's definitely a nice thing to have, to know that I can find a parametric representation of a curve that is not a function. Reason number two is that whenever a graph is being interpreted in parametric form, there is a direction of movement. There is a particular path on that graph. That's why I wrote over here direction of movement. In other words, points do not just randomly move across the graph. There will be a flow. The movement may either be in this direction or may be backwards in the other direction. And I'm going to show you how to determine the flow on that graph. This is when it may be useful to think of t, the parameter, as representing time. I usually like to think of t equals 0 as 0 seconds, 1 second, -1 second. Again, the negative just tells you that you are going to be on the left of 0. It's just right versus left. But you can still think of t being negative as -1 second and just on the left of 0. So, for example, consider a bug walking on that graph. When t is equal to -1 seconds, we found a while ago that the y value of this point equaled to 3. So at -1 seconds, here is the location of the bug. Then, when t was equal to 0, we found the location to be at the origin. So this pretty much seems as if the bug traveled through the graph starting at the peak and then moving nicely all the way to the origin. I'm going to go ahead and denote the path of the bug by putting arrows in this direction. Then, when t was equal to 1, we found that the location of that bug happens at the order pair 1, -3. That really means that if we continue moving the bug travels all the way up to here. So, denoting again with arrows pointing in that direction. If I were to continue plugging values for t, let's say that I try t equals 2, I will find that x of 2 is equal to 2 to the third, so that's going to be 8, and y of 2 is going to be 2 to the ninth minus 4, 2 to the third, which is going to give me 480. So then that means that the location of the bug will now be at the point 8, 480. Now again, here in this diagram, I only go up to 4. It is understood that the graph continues in that direction. So because I went only up to 4, I don't see 480. But then that means that when t is equal to 2, that point will be somewhere here above, pretty far away. The x value is going to be 8 and the y value is going to be very large. I don't have room to plot that here, but I think that you get the point. That really means that this bug will continue walking on this curve, moving in this direction all the way up indefinitely, just like that. So I'm going to go ahead and put arrows here, arrows and arrows. And if you try more negative values for t, if you notice, I only tried t equals -1, but nobody's stopping me from trying t equals -3, t equals -2. Let's see what happens when t is equal to -2. So when t is equal to -2, x of -2 will be equal to -8. Please remember that I am using the parametric representation of the curve. And when for y of -2, that will be equal to -480. And the way that I got -480 is I went and I plug in -2 for t here and -2 for t here. I did the algebra and I got -480. So then that means that when t is equal to -2, the order pair is the point -8, -480. On the graph, I can't even show it on the graph. I don't have enough room, but imagine that it ended up being somewhere here. So my point is all the way down over here at -2 seconds. And then at -1 seconds, I went all the way up right here. I could have tried also t equals -1.5. So I would have found the point to be somewhere here. So from -480, I go all the way up. I keep climbing on that graph all the way to a y value of 3. So what you find is that the direction of motion continues in the same way. So I go from down all the way up. Let me bring my bug. Let's follow the bug. The bug goes all the way up, reaches to this maximum here of 3. Then it goes down to the origin, continues to this low value of -3. And then it continues upwards all the way in that direction. So parametrically, the bug has a direction. It follows a particular path. It's not moving across the graph. And at every particular value for t, I can find the location of that bug. So I know that when t is equal to -1 second, the bug is there. When t is equal to 0, the bug is there. When t is equal to 1, it is here, and so forth. And reason number 3 is that I don't have to have a single parametric representation for the entire curve. I don't have to have that. I have more flexibility. For example, I may have a set of parametric equations that will give me this part of the curve. Let's call that C sub 1 of t. This set of parametric equations will have x of t for the x value of my point and y of t for the y value. And then I may have another set of parametric equations for the red part of my curve. Let's call that c sub 2 of t, which is going to be x of t comma y of t. And the x's and the y's are different. In fact, let me put subscript 1 here and y1 here so that we don't think that the expressions, that the parametric equations for x and y's are the same. These are different over here. So this is the parametric representation of the blue part of the graph, and this is a different parametric representation for the red part of my graph. With parametric equations, we can get crazy with these graphs. We can have different parametric equations representing different portions of the graph. Again, something that we cannot do with a rectangular representation of a graph. Let us summarize here the three benefits of representing a curve in parametric form. Number one is that the curve doesn't have to be a function to be able to be represented parametrically. Number two is that whenever a curve is represented in parametric form, there's always a direction of movement, there's always a flow. We cannot just be jumping around on that curve. And number three, if you have a complicated curve, a complicated region, you may need to have two or three different sets of parametric equations to be able to represent the entire graph. So you may have a parametric equation for one portion of the graph, another parametric set of equations for another portion, and possibly a third set of parametric equations for another region of the graph.